Hello, and welcome back to the third video of our case study series on the Clampock River. Today we'll be analyzing and modeling experimental data in MATLab. We will identify the values of BOD and O2 deficit at different segments using ODEs and visual plots. To recap, the goal of this research study was to determine the water quality of the Clampock River. This situation can be modeled as a plug flow reactor with contaminants. The re-aeration constant, Ka, and deoxygenation constant, Kd, will help us determine the reaction with the sections 3 in total of the stream being sampled. This research was conducted in the Clampock River flow Semarang district by taking 3 samples of river water in 3 different villages. From the previous video, we discussed the boundaries of the control volume of a plug flow reactor. Here we will walk through the calculations to derive the ODE we will use to calculate BOD, D, and O2. Mu is the change in velocity of the flow and can be simplified as Q over A, or flow rate over area. Mu is also equivalent to the change in D with respect to time. This will help us to sub in L for the first order rate reaction. If we have this equation in integral form, we can do some differential equation trickiness. Now we use our equation in the formula, divide all sides by mu, and end up with a rough form of our final equation. You can see the analogous form below. And now we have a final equation we're going to use to solve for BOD and D. The oxygen deficit is the saturation DO minus the actual DO. When the wastewater gets into the river flow area, which contains a certain number of BOD, the DO will automatically decrease, and it causes a decrease in oxygen. To determine the level of deoxygenation and re-aeration, we can use the Streeter-Phelps method as follows below, where Kd equals the deoxygenation constant, Ka equals the re-aeration constant, dt equals the oxygen deficit value in the pollutant source point at time t, Lt equals BOD concentration in milligrams per liter at time t, t equals the travel time between 2 segments, and this is in days, L naught is the BOD concentration at time 0, and D naught is the oxygen deficit value at T0. This mathematical model focuses on 2 phenomena, which are the process of dissolved oxygen reduction, which is Kd, due to the activity of bacteria in degrading organic substances in the water, and the process of dissolved oxygen increase, Ka, caused by turbulence in the river flow. This model was applied with a number of assumptions, including 1. There is only one source of pollution and no other input. 2. BOD decomposition rate is comparable to the BOD level. 3. Oxygen reduction is at the rate of BOD decomposition. 4. Oxygen addition is comparable to the decomposition. 5. The conditions along the water body are almost equal. And 6. A constant flow rate. Now we are going to use Ka and Kd experimental values at Clampock. These constants were for segments 2 and were obtained as the following values. Kd equals 0.226 per day, and Ka equals 0.162 per day. The value of Kd and Ka constants were used to calculate the value D and BOD value with the following equation, equation 1 that we used. I know this says 3, but it was equation 1 that we used 2 slides ago right over here. So we'll be using this equation to solve for BOD and D using our MATLab mathematical models. Here we have the code, and we're going to walk through some code to model the experimental data at segment 2. We'll start off by plotting the concentrations for L, D, and O2 at segment 2. T is approximated, I should mention that T is approximated by a very small increment, which is dx equals 0.001. The length x is measured in kilometers and can be calculated by taking that value t and multiplied by the average velocity mu. The other values are given. by the experimental data, L naught is 8 milligrams per liter, D naught is 7 milligrams per liter, the O2 saturation is 8.2 milligrams per liter. And now we have these equations, L and D, that we derived earlier. L is just a first order rate reaction using the inverse of Kd, which we are given over here. So that 0.226 per day will come back, and we will use that to calculate L. D will also be used by equation 1 as explained here. So we are just going to type that into MATLab with the following values: D naught that we established above with the constants. So if you type all that correctly and mind your parentheses, you can plot this on a concentration versus distance in kilometers, and you'll see the values of L, D, and O2, L being the BOD, D being the oxygen deficit, and O2 being the oxygen saturation levels. Next, we have the MATLAB code to model the experimental data with an analytical solution using the ODE 45 method. So again, we have the same values at segment 2, where mu is 0.37 meters per second, Kd is 0.226 per day, Ka is 0.162 per day, and we have the same increment value of 0.001, which is a small step to make that as close an approximation as possible. And then we have the same equations with the first order rate reaction, and then we have the equation 1 again. Now I'll be using ODE 45, which has the following syntax. So we'll be establishing a so if you follow the syntax, solving for one BOD and an oxygen deficit, then we can plot that with respect to each other. So we have L and D, and you get the following. So as you can see, based on the chart of oxygen reduction in segment 2, there is a decrease of oxygen levels in conjunction with the decrease in the value of BOD.